Hello there. Let's do some Wi-Fi, as it's become one of the most prevalent medias for connecting to a network, whether it be in a home environment or in an enterprise environment. So first, let's get going with the basics. Wireless LANs, or more commonly known as Wi-Fi, are defined by the IEEE 802.11 standard, and the specific name is wireless LAN. The name Wi-Fi is actually a trade name created by the Wi-Fi Alliance, which aimed at making wireless LAN technology a bit more accessible to the average consumer. Wireless LAN, or Wi-Fi as we know it, emerged in the 1990s, and the name was chosen to make it more relatable to people, as people would have a hi-fi system in their living rooms or lounges or whatever, and the name just made it a little bit less computery, a little bit less techy, a little bit more accessible to a consumer. But it actually stands for nothing. Remember, the term hi-fi means high fidelity, which describes an audio quality. And we don't use Wi-Fi for transmitting sound. We transmit data, which can be turned into sound by your phone or your laptop speakers, but we're not transmitting the sound itself. Now, in terms of how this works, it uses unlicensed ISM bands, or industrial, scientific, and medical bands. These frequencies are unlicensed internationally, which means you can use them for free as long as you don't use them for any sort of public broadcasting. The most commonly used frequencies are 2.4 GHz, 5 GHz, and the recently added 6 GHz, which is actually 5.9 GHz, bordering into the beginning of the 6 GHz band for some of the newer Wi-Fi standards. And nowadays, most client devices do support Wi-Fi, whether it be your laptop, your phone, your tablet, and even most modern desktop computers. So it is important that you understand the Wi-Fi standards and the amendments to them, so that you can predict your compatibility with your wireless access points. So first, we have the original 802.11 standard. Main frequency it worked at was 2.4 GHz, and it gave us a theoretical maximum data rate of 2 megabits per second. Just for context, this was mid-90s, and your average LAN cable is about 10 megabits per second. So at best, this was 5 times slower. Not very impressive. So the IEEE got to work very quickly on some amendments to do a bit of a better job. The first amendment to come out was 802.11a, and to get a high theoretical maximum bandwidth of 54 megabits per second, they went to the 5 GHz frequency. The problem is, though, going to the 5 GHz frequency meant there was zero backwards compatibility with the original 802.11 standard. And as you can imagine, people spent a lot of money on that standard and were very let down by the speed. So the IEEE also brought out within a few months the 802.11b amendment, which stuck to the 2.4 GHz frequency for backwards compatibility with the older devices and gave us 11 megabits per second. Not nearly as good as A's 54 megs, but still a lot better than the original 802.11 speeds. And then we got 802.11g a couple years later. Yes, there was a C, D, E, F, etc., but they were all signaling and stuff like that. This is mainly the speed standards you want to know about for now. And they stuck with the 2.4 GHz frequency and got up to 54 megabits per second. I got a feeling that the IEEE was dealing with people knowing that there was a 54 megabit per second standard, but not understanding why they couldn't use it. It was the frequencies that dictate the compatibility. Then, a couple years later, in the end of the 2000s, they brought out 802.11n, where we actually had both 5 GHz and 2.4 GHz available, and a theoretical maximum data rate of about 600 megabits per second. But realistically, you could expect between 300 and 400 megabits per second in a real-world implementation. Then we got 802.11ac, and there were actually two releases. So the first one got retroactively named Wave 1, where it was meant to work at 5 GHz only, but most vendors kept the 2.4 GHz around for the backwards compatibility benefit, offering us a maximum theoretical data rate of 3.4 gigabits per second. Although real world, you could expect to see about 700 megabits per second if you ran both frequencies, and about 1.2 gigabits per second if you ran it exclusively in 5 gigahertz mode. Then came 802.11ac's Wave 2, which gave us, again, 5 gigahertz as the main frequency for operation, and 2.4 gigahertz was kept around for backwards compatibility and lower costs. Theoretical maximum data rate of about 6.9 gigabits per second, but realistically you could expect anywhere from about 1.2 to 3.6 gigabits per second. In ideal circumstances, you could probably get close to the 6.9 gigabits per second, but it wouldn't do it very stably. And then most recently we've had 802.11ax, where we've got 5 gigahertz and 2.4 gigahertz being kept around for compatibility, but this time it's not requiring us to go into a pure 5 gigahertz mode to get the best performance. And 802.11ax promises us 9.6 gigabits per second. Now, with all of these annoying 802.11 letter acronyms, the Wi-Fi Alliance decided to come up with this generational naming scheme retroactively to make it easier for consumers to keep track of things. Similar to what we do with cellular networks, we have 3G, 4G, 5G. They created the Wi-Fi generations, and they decided to start by giving 802.11ax the name Wi-Fi 6, and then retroactively worked their way backwards to the older standards. AC got Wi-Fi 5, 802.11n got Wi-Fi 4, 802.11g and A got Wi-Fi 3 because this is all being based on the speeds. 802.11b was Wi-Fi 2, and the best forgotten original standard 802.11 got Wi-Fi 1. Now, before we get too carried away with how Wi-Fi infrastructure works, let's get some key terminology dealt with. First of all, I've already started using this one, the access point. It is the device that provides the wireless signal and connectivity that the laptops, phones, and etc. can connect to. Wireless access points are considered OSI layer 2 devices, as obviously they do the radio frequencies for the physical media, but they also do understand a bit of layer 2 data encapsulation so that they can properly structure, coordinate, and communicate effectively. Now, your wireless access points create an area of coverage called a basic service set. Some people call it a basic service area, but it is essentially the radio signals propagating out, providing the opportunity for wireless connectivity for end devices. Then we have the SSID, or Service Set Identifier. This is the string of text that is the name that you give your wireless access point. For in this case, we have Bob Wi-Fi, because I'm very original that way, I know. It is going to be the text that you see when you're busy looking at what wireless networks are around you that you can connect to. However, there is another identifier that your phone, laptop, etc. likes, and that is the Basic Service Set Identifier. That is the access point's MAC address. Now, the access point's MAC address is usually not shown to you on your device, but your device does see it. So if any of you have ever tried this, where you got a new wireless router at home, and you thought you'd set it up exactly like your old one, same SSID, same security, same passphrase, everything, hoping that all of your devices would automatically connect to the new one, and they didn't. And the reason why is because your devices saw a different BSSID or MAC address, and they were like, nope, I'm not falling for this. This could be an attacker trying to impersonate my real access points I've previously associated with. So it's actually kind of good that you can't quickly and easily replace your access points like that. Otherwise, a lot of people would have their devices hacked very easily. Now let's go and understand how Wi-Fi deployment technologies work for us. So you're going to hear about this thing called an independent basic service set. It is essentially an ad hoc wireless network where a bunch of wireless devices, like laptops in this case, establish a peer-to-peer wireless connection with each other. We call this ad hoc because the network is set up as needed and is mainly aimed at local file sharing. The intent here is not to provide access to proper network infrastructure or internet connectivity. If you want to do that, you might want to go with a more basic service set infrastructure mode deployment, where you have your wireless access point that your client devices associate with. and then that access point will somehow provide connectivity to the rest of the network infrastructure. That method of doing that is called a distribution system, and it is the way the access points connect you to the rest of the network. There are two main kinds of distribution systems that you would encounter. The first one is a wired distribution system, and my personal favorite. But you also do get wireless distribution systems. And just to be annoying, there are two types of wireless distribution systems, a relay and a mesh. So first, let's have a look at a wired distribution system. This is where we're going to have our access points and some ordinary network infrastructure, and the APs are going to connect to that infrastructure with a network cable. Essentially, the wireless only exists between the clients and the access points. Now, the reason why this is my favorite is because the cable that connects the access point to the rest of the network provides a more stable and higher performance connection upstream, and also helps a bit with the security side of things. And my other reason for liking this is it gives me more choices in how to power my access points, because I can either power my access points via a nearby wall socket, or I can use the network cable, as long as I can do power over Ethernet, to the access point. Something we'll talk about in a later video. Now, when you are doing a wired distribution system, this is normally going to be considered a permanent installation, so you don't do this for like a temporary thing. If this is your home or your office, go for it. But if this is like a convention center or a showroom floor, might not be perfect for that kind of scenario where you might be setting up and taking down that network on a regular basis. If you want something more temporary or more flexible, a wireless distribution system might work a bit better. So first, let's deal with the relay method. We're going to have a couple access points and a switch again. And what will happen is the access points will wirelessly relay to one another. So the access points will send wireless signals to one another, and then one of the access points will have a wired connection taking it to the network infrastructure. And there will be a lot of wireless between the clients and most of the APs. The catch here is this is going to be a less high performing and less stable connection, as you are relying now for wireless both from end user to access point, but also access point to access point to access point for however long you want to relay this for. And it also does take away your ability to have choice in power. You have to rely on wall sockets for power. You will not be able to do power over Ethernet because there's no cable to most of these access points. And we usually do this for a temporary network installation or situations where running network cables is not an option. But we also have wireless mesh networking as another kind of wireless distribution system, or a WMN. Now here, we have something very similar to the relay where a lot of the access points are going to be relying on wireless connectivity. However, we will have many APs forming a mesh topology connection with each other. In other words, they will try and establish a direct wireless connection with all nearby wireless access points. This does a few interesting things. First of all, it saturates the area with wireless signal and allows for a better level of stability than the relay-based wireless distribution system. The reason being, if one of these access points becomes faulty or if there is a point of interference nearby, there will be a way around this. Now, I still personally recommend doing a wired infrastructure if you want better stability and better performance, because then all of the wireless bandwidth can be made available for client connectivity with a wired distribution system. Now, an important thing to do with wireless mesh networking is all of the access points must support the wireless mesh standard of 802.11s. The way I remember it is 802.11s is my wireless mesh standard, with an emphasis on the S. And preferably you want to try and make sure all of the access points are the same make and model to maximize compatibility and chances of success. But this is a very popular way of maximizing wireless coverage in small office, home office network environments. Now, another interesting feature of wireless access points is how they support connections. So first, let's start with the original type, which was never actually given a name. until a successor technology came along, and then we came and retroactively called this SISO, or single input, single output. So if you can imagine your wireless router or your wireless access point with this antenna and a couple clients, what would happen is you could either be receiving something from your wireless access point or sending something to your wireless access point. The older wireless LAN standards, basically everything up until and including 802.11g, work like this, where one person at a time would either send or receive. So yes, technically, wireless LANs were originally a half-duplex kind of media. But around the 802.11n era, MIMO, or multiple input, multiple output, came along. And what happened here is access points started showing up with more than one antenna. The purpose of the extra antenna was to allow for somebody to receive something from the access point and send something to the access point at the same time. And this was done via two antennas working on separate spatial streams within a Wi-Fi channel. It's a pretty cool benefit. And this gives us the ability to emulate full duplex. However, it would only work for one person at a time. So around 802.11ac wave 2/AX, we started seeing MIMO, or multi-user MIMO. So officially 802.11ax introduced this, but it was experimentally brought in with 802.11ac wave 2. Now what happens here? More antennas. Sometimes, yes, your access point will have that many antennas, although sometimes you might not see them. They might be internal, or they might be built into one single rubber antenna. You don't always see the conductor inside. And this will allow two people to both send and receive stuff from their access points, which I think is wonderful, as this allows for more people to have full duplex like communications and get wireless communications done more effectively. Another nice benefit of MIMO is that it also helps alleviate capacity problems, as more people can communicate at the same time, meaning we can have more people in standby and not having to wait too long before they get their turn on the Wi-Fi. But you still obviously do run into capacity issues. So one of the common symptoms would be that performance deteriorates drastically. If you have a lot of people on the same access point, it might be that you need more APs. Capacity will always be a major challenge with access points and wireless. Now let's look at the SOHO style of implementation, or small office home office. So the small office home office implementations are considered autonomous access points, which I'll explain properly just now. But basically, configuration on one device is what autonomous only means. But your home network normally uses a wireless router, which is a combination device or appliance, as yes, it is a router. It also includes some sort of modem usually, has a wireless access point, a switch, and a DHCP server built into one discrete appliance. Now, in some situations, your modem might be an external device. It depends on the type of internet infrastructure you are gaining access to. But for a lot of people, it might be an internal modem as well. It depends on your network and your ISP. But in a small office, home office environment, you can substitute this with additional wireless access points. And you can do this by either linking them up to your router's switch ports with a network cable, or using wireless repeaters, which I'm not overly mad about, as the repeater is positioned some distance away, receiving a weaker signal and then relaying that signal further down. The problem is, though, the people that rely on the wireless repeater are going to experience lower bandwidth compared to the people that are on the proper wireless access point. So if you can, try and run wired cables for your extra wireless access points. The performance bonus is definitely worthwhile. But when you get to the enterprise access points, they get quite interesting. They can either run as autonomous access points or as lightweight access points. The choice is yours. But with enterprise access points, they are wireless APs only. They will depend on network infrastructure at some point for the routing, the switching, the DHCP, etc. And usually in the workplace, you are going to be implementing more than one access point to provide coverage throughout the entire workplace. So let's check it out. Here's some access points and a switch and a router. if we were to run them as autonomous access points. What this means is that the APs are going to operate independently of one another, and they will also be configured independently of one another. This is pretty much what your small office, home office access points are like. And I'd advise you to keep these guys down to a minimum, at least in the workplace, because you are going to be logging into each of these access points individually and configuring them individually. Now in my diagram here I've got 3 of them, which doesn't sound like too much work, right? But in an office building, you might have dozens or hundreds of these things. And if you've got to configure each one individually, this is going to get very frustrating very quickly, and you're also going to get very bored while you're doing it. And when you're getting bored doing a mundane repetitive task, that's when your brain goes on a holiday and mistakes happen, and it becomes a lot harder to find that 1 or 2 access points in dozens or hundreds that you made a mistake on. So in a situation where you're going to have a lot of wireless access points, it's going to be a lot better to do a lightweight or managed style of access point, where the access points are going to depend on a wireless controller appliance to coordinate them. Now, depending on the network vendor you go with, this appliance might go via several names, but I have seen things like access controller, wireless AP controller, wireless LAN controller. Nonetheless, though, the name's going to imply it controls wireless access points. Now, we haven't really got a proper official symbol for it just yet, so I've gone with a bit of an amalgamation of what I've seen most vendors using. Now, what's cool about the controller appliance is it's set up to distribute the configuration to all the access points via a specific protocol. In a lot of cases, the protocol used is a proprietary one, so you're going to have to match wireless access point vendor with the controller. But the coolness is you get all of the access points enrolled or added to the controller, and you go and do your configuration on the controller once. And then it propagates throughout the network and applies to all of the access points in one go. And the great thing here is that work gets done once, and it's a lot easier to be focused for that. And if you do make a mistake, well, at least that mistake is going to be applied consistently, and you know exactly where to go to fix it. So that's pretty cool. Now, another nice benefit is also the access points will be coordinated to work together, which means things like roaming between access points will be possible. And you could even get the same SSID being sent through to the client, and they think they're connecting to one massive access point that covers the whole building. So things like roaming and that are going to be awesome to have. And the roaming will allow people to move from one access point's coverage area to another's without losing connectivity. It'll usually end up looking something like this, where the multiple access points are going to have some overlapping coverage, and we get them to work with the same SSID. Now the user sees that one big SSID, and this is what we call an extended service set identifier. And the full coverage of the building is now called an extended service set. Now, yes, the client will see different BSS-IDs, but when the client queries the access point saying, hey, do you know this person nearby running with your SSID? The access point will say, yes, I do, it's my friend that is being managed by the same access controller as me. You can trust them. And that will allow them to roam from access point to access point. Now, with this overlapping coverage, obviously we don't want interference to happen. We want people to be able to recognize when they're talking to this access point, when they're talking to that one, and when they're in this area of overlapping coverage. So that means we better start talking about wireless channels. So the idea of a channel is it takes the frequency bandwidth and divides it up into smaller segments. It's sort of like when you want to watch TV and you've got a subscription service, whether it be cable TV or satellite TV or whatever. You dial in a number and you tune into that channel. You don't accidentally see what's on the channel before or after the one you dialed into. And that's what we're hoping to achieve with these wireless channels. Now, the IEEE took the 2.4 gigahertz band and divided it up into 14 channels that are 20 megahertz wide. And here is a visual representation of them. Now, there's a bit of a problem with how they did this dividing. Most of the channels are overlapping, which means that if I have an access point working on channel 2 and channel 3, on the next access point, there's a lot of overlap. This is going to mean that when there's coverage overlap, with the basic service set of the two access points, the clients are not going to know whether they're talking to access point 1 or access point 2. Not a good situation. Thankfully though, there are 3 channels that are pretty guaranteed to not overlap, and that is channels 1, 6 and 11. Now there might be a different arrangement of channels depending on where you are in the world, as every country's got their own radio regulatory body which dictates how these frequencies may be used. But for the most part, channels 1, 6 and 11 are the guaranteed not to be a problem no matter where you are in the world. So that means I can have 3 access points nearby, one of them running on channel 1, another one running on channel 6, and another one running on channel 11. And they don't cause problems for each other, because the channels are far enough apart that there's no signal overlap. The question though comes in, what about when I want a 4th access point? Well, now I've got a problem, right? Not really, as I just need to go and put channel 1 on that access point. Now it's fine to reuse channel 1, because this new access point is too far away from the other access point running channel 1. So there's not going to be a problem. If I wanted to add a 5th wireless access point here, over here, I'd probably go for channel 11 as it's quite far away. As long as you strategically choose which channels you use where, you're normally going to be in a very good position. Thankfully though, the same mistake was not made with the 5 GHz channels. We've got 24 channels, although in some countries it might only be 23, that are also 20 MHz wide, and this is what they more or less look like. Now what's pretty cool is, as these channels do not overlap, something called channel bonding is doable. Now what happens with channel bonding is I can tell my access points to take 2 neighboring channels and make them work together as a 40 MHz wide channel. And that actually increases the bandwidth for that access point, making it transmit data quicker. This is something that was introduced with 802.11n and kept getting innovated on, where we can make 40 MHz wide channels, or we can take a pair of 40 MHz wide channels and make an 80 MHz wide channel, or a pair of 80 MHz and make a 160 MHz wide channel. It's pretty awesome. And the channel bonding is one of the reasons why we saw such big speed jumps happening from A2 to 11G to N to AC to AX. So that's pretty nice. What's even nicer is wireless security. And the reason is security is nice for everything. So let's talk about wireless encryption and understand where it exists. So first, let's have some network infrastructure. So have a laptop and a wireless access point. Obviously they connect to each other wirelessly. The access point is then going to be on a wired distribution system to a switch and a router. The router is going to take me to the internet, and the internet is going to take me to a server I want to talk to. Now the important thing to understand is that wireless encryption exists on the wireless infrastructure between the client and the access point only. If all I have protecting my communication with something like a web server is the wireless encryption, then my traffic is only being protected while it's traveling through the air between the laptop and the access point. We need to rely on something else, like HTTPS, to provide proper session-level encryption all the way from the laptop through the infrastructure to the server we're talking to. Now, this doesn't mean that wireless encryption standards are not worth having. It just means that you must appreciate they only work to protect the data while it's traveling from the client to the access point. Once we hit other kinds of network infrastructure, we got to rely on other kinds of encryption. Effectively, what wireless encryption is trying to achieve is give the same level of privacy and surety that we get with a wired network connection. So let's have a look at some of the common wireless encryption standards. So first, let's have a bit of a scale where we go from weak to strong. Now, I'm going to warn you, I'm going to give you quite a few wireless encryption standards, some of which CompTIA doesn't want me to tell you about, but I'll explain why now. So first you have open access, which means that the access point's open. If you can see the SSID, you can click it, you can tap it, you can connect, and off you go. But everything you'll be transmitting will be in clear text, unless you've got an upper layer protocol performing encryption on the payload, like HTTPS or POP3S or something like that. Then the first form of wireless encryption introduced was WEP, or wired equivalent privacy. Now, WEP encryption came out very early on in wireless's life, so as you can imagine, it's an old encryption standard. But at one point it was the best we had because it was all we had. But by modern standards, web encryption is not very strong. It will take the kid next door 10 minutes and a YouTube video to figure out how to crack your wireless encryption if you're using web. So if you've got no alternative, well then, yeah, it's better than nothing, but it is only that, just better than nothing. Now the problem is web came from the IEEE. So as an interim solution, the Wi-Fi Alliance created something called WPA. We now call it WPA1 because newer variations use a higher number to indicate they're newer and better. Now lately, CompTIA has been getting a bit freaked out and doesn't want us talking about these older standards. So things like Open Access, WEP, and WPA are not in the Network Plus exam anymore. This is more for your knowledge in the field. Now the reason why I want you to know about this is if I only tell you about what CompTIA wants in the exam, and then one day you're setting up wireless infrastructure for somebody and you see WEP, you're like, ooh, what's this WEP thing? It's new to me, must be new and more secure, when actually it's old and worse. It might be new to you, but it doesn't mean it's new and better. So basically, I want you to be properly informed and know that that's a setting that is still available. It's there for legacy purposes and other weird situations where you might not be able to use a more modern, sophisticated and elegant form of wireless encryption. But now for something that is in the Network Plus exam. You've got WPA2 and WPA3. Please be aware WPA3 came out with 802.11ax or Wi-Fi 6. So you do need to be using modern wireless access points and modern clients to take advantage of it. But even if you can't, WPA2 is still pretty decent as long as you've got a good passphrase or you've gone for a fancier form of wireless encryption called enterprise mode, which is what I want to tell you about next. So your wireless encryption standards can either be running in something called private mode or enterprise mode. Private mode is sometimes known as pre-shared key or PSK mode. And what happens here is we usually use a passphrase as a form of authentication and encryption. Now, the way it works for authentication is that we should only be telling people who we want to have on our wireless network what the passphrase is. So it's sort of like a secret password to get into a special club or something like that. But there is a bit of a problem as it is a shared secret. So if one person shares the passphrase to somebody they shouldn't, well, nothing stops the next person sharing and sharing and sharing. But as long as that passphrase is kept secret, you're okay, sort of. And it's also used as the seed value to generate the cryptographic keys that will be used to encrypt and protect the data being transmitted. This is very common for small office, home office networks and simple enterprise networks, as it doesn't require much additional infrastructure, just a very well chosen passphrase. And the cool thing is, a good passphrase usually is very similar to a good password. Long, complex, difficult to guess, that usual stuff. But what about this enterprise mode? Well, enterprise mode is also referred to as 802.1x mode because it is based on the IEEE 802.1x. Now, 802.1 is the IEEE's standard for LANs. Please don't confuse that with 802.3, which is the IEEE standard for Ethernet, which is a format for structuring data on LANs. 802.1 is always going to be around. Now, 802.1x specifically is what we refer to as network authentication, where we want people to authenticate before they join the network. So this is going to rely on a AAA server, or an authentication, authorization, and accounting server. The popular types of servers we can use for this is a Radius server, or a TACACS Plus service, or it could be any variation of TACACS, and any other 802.1x compliant authentication services. There are some LDAP directory servers that you could actually use for 802.1x as well. Now we will talk about these types of servers in a later video to do with network security. But the idea is it's going to allow for individual user authentication and authorization accounts. In other words, every user logs into the network with their own password, which is pretty cool. And it can also provide various options for authentication and encryption, which means the encryption key per person could be slightly different, meaning that if an attacker finds a way to compromise one person's wireless encryption, it doesn't mean everyone is compromised, just that one person. And then, very easy to forget about, we have got the ability to account or log the activity. So we can keep track of who's connecting, what device they're using, what they're transmitting. There's a lot of options that we can have, most of which are dependent on the server we use, but still the ability to keep track of what users are doing on the network to some extent can be pretty useful. Now, in terms of these enterprise and private modes, it is available for WPA, WPA2 and WPA3. So when you're deploying your wireless access points, whether it be at home or at work, you will usually see private and enterprise or PSK and 802.1x mode for all three of those encryption standards. Use the one that's the most appropriate, obviously. But something to understand is we also get these transitional encryption standards. Two are currently seen in most wireless access points at the moment: WPA2/WPA and WPA3/WPA2. And the idea is that it allows an access point to revert to the older encryption standard if a client is unable to support the newer one. Now, around the time when WPA2 first came out, most people's wireless clients were WPA only. So it was nice that we could run the access point in that mode where it would try to do WPA2 with everybody, but if the client couldn't do WPA2, the access point would drop the encryption down to WPA for those clients that couldn't handle it. And guess what? We're in one of those periods right now where WPA3 is still very, very new and not everyone's phones, laptops, etc. supports it. So it's nice that the access point can run in WPA3 mode for those who can support it, and for the devices that can't, it drops itself down to running in WPA2 mode. It does make the access points a little bit vulnerable because obviously it's supporting the older encryption standard, but you've got to strike a balance between usability and security, I'm afraid. And there's no point saying our network is super secure, but hardly anyone can use it. But we also have another interesting way of authenticating and encrypting connections, and that is a captive portal. So what happens with captive portals is the access point will present itself as an open access point. The user will then connect to the access point, but the access point will not allow them to communicate at first. It'll trigger a browser to pop open on their device, and that browser will display a web-based login page. Now, what the login page asks of the person connecting, well, that can vary. It could ask for a username and password, it could ask for a special token, it could ask for anything. But what this is going to do is it's going to force people to provide the network some information about themselves. And that will allow us to identify and recognize new devices and figure out which users they belong to. Or if this is a coffee shop or a restaurant or a hotel, it could be very easy to check that this is a customer or guest that is actually meant to be connecting. What's pretty cool about a lot of the captive portal systems I've seen is that they can do encryption at higher OSI layers. So they can keep all of the traffic encrypted through the network infrastructure up until the thing that runs the captive portal. Remember, the wireless encryption standards like WEP, WPA, WPA2 and WPA3 are between the access point and the client only. This can happen at a higher layer, which the access point will not see. In some cases, the client won't see it either. So if you ever are connecting to a captive portal network and it says, unsecure or open, it might actually be encrypted just at a level beyond what your wireless network card and operating system were expecting to see. Now, an important thing to do with your wireless infrastructure is to make sure you document it properly. The reason why is because you can't see the radio waves, sadly. Unlike your network cables, where I can actually see if a network cable is running from point A to point B. It's a bit harder to track and trace things that are invisible to us. So let's talk about things that makes for good wireless documentation. And the first thing is a site survey. So a site survey is done by visiting a premises to view it and make plans for either a new wireless deployment, an upgrade to an existing wireless deployment, or an improvement to an existing wireless deployment. Now, the most important thing I can encourage you to do is to not rely on any previous documentation. for a site survey. Whenever it comes to new deployments or upgrades to existing ones or improvements or extensions, even if previous site surveys have been done, you go there and you validate it. You make sure that everything is correct. The reason being, the floor plan may change. There might be new kinds of furniture or structures in the space, or any other kinds of undocumented changes to the network. All of this would essentially invalidate the previous site survey. So yes, by all means, look at the old one, but don't take it as guaranteed that is how the network is. Go prepared to do a brand new floor plan, signal map, everything. Now, in terms of performing a site survey, either make a floor plan or adjust an existing one. Pay special attention to the building, the structure, the furniture, and the materials they're made out of. The reason why is all of these things are going to affect how wireless signals propagate. Dense materials like concrete and thick wood will do a lot of absorption of signal. Metals and some ceramics will reflect wireless signals a lot. So you want to be able to identify from the floor plan how thick that material is and what it is to get a rough idea about how much the signal might decrease if it's trying to travel through that. And also note infrastructure. There might be wired infrastructure that you can plug into, and you also want to make a note of power for where you'll power up your access points, or if you can rely on the network infrastructure to deliver power over Ethernet. So make sure you annotate that on the floor plan. Now, coming from experience, my best advice is take photographs, lots of them. Because if you rely on your memory, I guarantee you've either forgotten something or you will remember it incorrectly. Take photographs, and as many as you can, while you're on site. Even if the site is one floor down in the building, do yourself a favor, take a photograph, that way you don't have to keep walking back and forth. You'd be amazed the amount of times that this can help you out. I know it definitely did for me. And if you can, use a test access point to verify signals in the space that you are planning to deploy your wireless network. And if you can, try and observe the users. Where do they work, and what kind of things do they do? What are they using the network for? If you can observe that, it helps a lot as well to plan your wireless network out. Now, the two reasons why is because, first of all, where users are going to sit is where you probably want to make sure you've got very, very good wireless coverage. Extra access points, stuff like that. And also what they're using the network for. Are they just sending emails? Are they doing a lot of teleconferencing? Are they doing a lot of uploading, downloading, streaming? What's going on? If you can see what they're doing on the network, that gives you an idea about how much capacity you must make sure the wireless network has. Now, another important thing to do as well is to make sure that you keep the asset inventory up to date with the wireless infrastructure. You want to make sure that you add the access points make, model, and quantity to the asset inventory so that you can keep track of the products that you have, so that you can know what you have when it comes time to upgrading or replacing. Also, make a note of the access points MAC addresses, as that is a very, very common way for the controller to identify and manage the access points. Also note the serial number, very, very useful, also for the wireless controller, but the vendors also want to know it as well for warranty purposes. And any documentation from the vendor for supporting their products and services, you make sure you want to download that and keep a copy of it. Never rely on a vendor's website always having that data available for download. The thing is, people go around and say the internet is forever. And yes, stuff on the internet can be forever for as long as someone is prepared to host that page. But hosting web pages costs money. So, in short, the internet is forever until it's not financially viable, and then it's not forever. So do yourself a favor, don't rely on a company keeping a website up for an old product so that somebody might one day be able to download a technical support PDF. Keep your own copies of the stuff. At worst, it turns out you might never need to. But the day it happens where you need that PDF and the vendor's website no longer has that AP there, you'll be very glad you got that local copy somewhere. And then make sure that you note the location on the floor plan where the particular access point is going to be found. Again, one of the favorite things I've always encountered with asset inventories is people keep track of the details, but they don't keep track of where it is, which then comes to the problem of, okay, but where is it? How do I know which one I'm replacing? Then comes heat maps. Heat maps are pretty cool because these are visual representations of the wireless signal overlaid on top of your floor plan, so that you can get a rough idea of what the signal propagation looks like in the workplace. Now, when it comes to doing it, it doesn't need to be a fancy three-dimensional diagram like I've got here in the picture. If you can do that, though, it does look pretty cool, I won't lie. But it can be a simple, flat, top-down floor plan access point with wireless signals propagating throughout. Now, to do this, you can either use dedicated tools, or you can manually measure them and overlay it on top of a floor plan. Now, if you go for the dedicated tool option, you can go and look on Google or whatever your preferred search engine is for wireless LAN heat mapping or Wi-Fi heat mapping software, and you'll come across loads of them. The reason why I don't want to make any recommendations or name drop here is because some of them are paid for, and I don't want you spending money or spending your company's money without properly investigating and reviewing the solution first. If you manually measure it, it's going to be a little bit of an annoying process to do because you obviously have to move around, measure, and make notes on floor plans and stuff like that, and then consolidate all of that into one diagram, but it can be done. Now, in terms of measuring signal, you still want to do this because it's going to be useful to look at what signal strengths look like at different times of the day, different times of the year, and just to try and do a little bit of physical troubleshooting on how the radio frequencies propagate. Now, you can use a radio frequency spectrum analyzer. This is a purpose-built wireless measurement tool that can detect not just the wireless frequencies, but also frequencies next to the ISM bands that could be causing interference. The problem, though, with an RF spectrum analyzer is it's a purpose-built tool, very sensitive, very capable, very accurate, and costs a lot of money for that. More money than most organizations are prepared to spend on measuring wireless LAN signals. So a cheaper option is an application on a wireless client. Now, you can either run it on a smartphone or a laptop. The apps exist in plenty, and again, same as before, I'm not going to name drop any products or services because I'd rather you go and find it on your own and make your own informed choice about which one you want to use. But they are going to be less capable of detecting the neighboring frequencies that could be the sources of interference, but it's a lot cheaper still. And the only variable you really got to worry about is how good is your wireless network adapter. A good rule of thumb, though, is your phones generally have less sensitive, weaker wireless adapters, so the signals are going to be weaker, and you will start seeing a drop-off in received signal strength a lot sooner with a phone. Compared to a laptop, laptops usually have much more sensitive and stronger received signals, and will therefore be able to pick up on wireless signals for a greater distance than your smartphones can. So if you're going to use the apps on a client, the idea is have both a phone and a laptop. And in one location, what you do is you'd note, okay, the phone would be my minimum expected and my laptop would be my maximum expected received signal strength from this particular position in relation to the access point. But that is all I have for you guys for the Wi-Fi. Now, in terms of wireless LAN support, believe you me, it can become a very, very involved thing. With some of the network vendors I work with, they've got entire courses and tracks dedicated to wireless LAN administration. So there's a lot to it if you want to get into it properly. But this should serve as a fantastic foundation. As always, I'd like to say thank you for watching. I really do appreciate it. And if you have any friends, family members, peers, etc. that would like to learn Network Plus, don't be afraid to share this video with them. Otherwise, though, I will catch you in the next video.